the invitation. Allow me have the chance to present the talk entitled Recent Progress in Wide Bandgap Semiconductor Power Device. My name is Tian-Li from National Yangming Jiaotong University. Okay, so first, this is the outline for today's talk. First, I will introduce the wide bandgap materials and devices. And second part will be the main topic for today is I will review the recent advance in the wide bandgap power device. Especially, I will put the main focus on the three different, very promising next generation power semiconductor device. The first one is the gallium nitride, and second one is the silicon carbide, and the third one, the gallium arsenide. Recently, in the last 5 years, is gallium arsenide power device attract lots of the attention because due to the large wide bandgap, and also in the last 5 years, there are tremendous progress in the gallium arsenide power device as well. So I will present some of the recent progress, and final is a conclusion. So first, I will give the general overview for the wide bandgap materials and devices. And from the periodic tables, as you can see here, the group 3, 4, 5, the material, the chemical species in group 3, 4, 5 are the most important species to form our semiconductor device. And therefore, by combined with the different species, actually we can start to make different kind of the semiconductor materials. And then therefore we categorize with 4 different types based on its material properties and application. The first type is a conventional one, which is the silicon and germanium. And these are still the main dominating semiconductor material for the low power technology, especially for the cell phone or even for the logic application. We still mainly use a silicon-based semiconductor device and electronics. And regarding for second type is considered as a compound semiconductor that we combine, for example, gallium arsenide or indium phosphide. And these two material has been widely used for the high frequency. But however, this material has a very small band gap. So that's why we can only use for low power application. In the last 20 years, there are tremendous progress in the gallium nitride and silicon carbide. These are compound semiconductor device. And gallium nitride and silicon carbide feature with a wide bandgap material. The bandgap is more than 3 electron volt. So therefore, it's very suitable for the high power application. Especially gallium nitride also has a 2-dimensional electron gas, so that's also very suitable for the high frequency application. So in overall, right now the gallium nitride and silicon carbide are very promising for the high frequency, high power, and high efficiency, and also silicon carbide has a good thermal dissipation, and also nowadays the wafer size for the GaN and silicon carbide has been already have large 8-inch wafer size. And then the last one is in the last 10 years, the gallium arsenide based material are very promising and has been developed toward the mature level that we can start to make the gallium arsenide a device. So gallium arsenide is what we generally call as an ultra wide bandgap material, has a bandgap more than 4 electron volt. So gallium arsenide is very suitable for the high power and also for high efficiency power electronics. And nowadays, we already have large 4-inch gallium arsenide wafers. So if we try to compare the several important material properties, the first one is a GaN bandgap. So basically, we can find that the silicon carbide, gallium nitride, and gallium arsenide both has a larger bandgap than silicon. It has a 3 times larger. So generally, we call this as a wide bandgap. And gallium arsenide, sometimes people call this as an ultra wide bandgap material. And another important material property is a critical electric field. So silicon carbide has a 3 megavolt per centimeter, and gallium nitride has a 3.3. And the interesting part for gallium arsenide has a more than 7 megavolt per centimeter critical electric field. So generally we have the lot more than 10 times larger than silicon materials. And last one is electron mobility. So gallium nitride feature with two-dimensional electron gas. So generally gallium nitride has a better mobility than the silicon. Of course, silicon carbide and gallium arsenide, the disadvantage of these two materials is generally has a lower mobility than the silicon. So if you try to put all these material property in the theoretical calculation by considering the on-state resistance versus breakdown voltage, so generally we can see the silicon limitation is around here, and silicon carbide is here, and gallium nitride and gallium arsenide are all around here. So if you try to put all those materials property as shown in the previous slide, generally we can have this on resistance. So what we can find is that within the same specific application voltage, silicon carbide has 100 times lower on resistance, and gallium nitride and gallium arsenide has 1,000 times lower on resistance compared to silicon device. So this superior characteristic make that if we use a silicon carbide, gallium nitride, or gallium arsenide power device, then actually we can achieve more than 50% reduction of the switching loss, and that can save some of our energy, can improve our energy efficiency, and then reduce energy lost during the power converting. So before we continue to go through this material, and one important thing is to understand that the material sometimes has a different crystal structure. Some crystal structure exhibit as a non-polar materials. And by consider non-polar material, we can make a typical junction transistor by consider a different doping, different the contact type, we can make the junction transistor. But if we consider the material has a polar properties like the gallium nitride, so we can not only make the junction transistor, but we can also make the hand, this kind of structure that we generally call as a high electron mobility transistor. So one of the most the important things to compare with the gallium nitride power hand and silicon carbide power MOSFET I will be shown in this slide. So basically, we can find out that the gallium nitride hand is an electro device. And most important property is that we don't need any doping involved. So that's a big advantage for the manufacturing. And also because due to the different polarization, especially the spontaneous polarization and piezoelectric polarization, so the high mobility can naturally form in the interface between L-GaN and GaN. So therefore, we can have very high mobility at this interface, even we don't have the specifically doped channel. So that's a big advantage for gallium nitride power hand. But if you compare to silicon power MOSFET, we can find out that basically silicon power device, silicon carbide power device, it has a vertical device structure. That means we have a drain in the bottom, and we have the source and the gate on the top. And then the carrier movement is along the vertical way. So that's what we call the vertical devices. And we needed to have the doping to form the PN junction. So we need to use this PN junction to sustain the high blocking voltage. And right now, there are the two main streams for the silicon carbide MOSFET. One is silicon carbide D MOSFET, and another one silicon carbide U MOSFET, which is a trench MOSFET. So although gallium nitride exhibits very promising high mobility between the L-GaN and GaN, but if you consider for the real application in the market, actually our power semiconductor market demands for the enhancement mode device. So that means when we grow the gallium nitride hand, if we don't do any process, and then the gallium nitride hand exhibit as a depletion mode characteristic, that means our threshold voltage is below 0 volt, and therefore to fit the current needed for the power electronics, actually we prefer to have an enhancement mode characteristic, as shown here. And there are the two main rules for the enhancement mode device. One is we can consider use a cascode with a silicon FET. So that means we have the one low voltage silicon FET in series with a high voltage demo gain ham. And that we can realize a normally off characteristic. Or on the other hand, we can also directly make a true emo device. So one example here is we can have the P-type gallium nitride on top of L-GaN, and this P-GaN will deplete these two decks under the gate and realize the enhancement mode characteristic. So far, we have several main types for the gallium nitride power device in the market. Of course, in the beginning, when we just grow the gallium nitride hand epitaxy, it exhibits as a D-mode, depletion mode characteristic. And then with these two several approach, we can realize the enhancement mode. One is we can realize by using the P-type gallium nitride gate on top of the L-GaN, then we can have the enhancement mode characteristic. Another one is we can do the etching to etch away the L-GaN and then to interrupt the two deck between the source strand. Then we can also realize the enhancement mode characteristic as well. And another one is also very popular approach and already in the market now is by using the cascode with silicon FET. So these three approaches are the most three common approach people try to develop enhancement mode gallium nitride hand. And another, on the other hand, regarding to the silicon carbide power device. So in the beginning, we can purely by leverage these fully vertical silicon carbide epitaxy to fabricate silicon carbide Schottky diode, and silicon carbide Schottky diode has been already commercialized in the market for the decade. And then recently, people start to put more attention on the silicon carbide planar MOSFET or silicon carbide trench MOSFET. So regarding for the planar MOSFET, we actually form the channel around this region, so the electron can be flow from the source to the channel and then in there inject to the drain. And that's why we call this as a planar MOSFET, because the channel is in the lateral. And on the other hand, we can also fabricate the trench MOSFET, where we will etch away this region and fabricate the vertical channel, and therefore the electron will flow from source through this vertical in the end to the drain. And the one of the attracting advantage for the U MOSFET is that we can achieve very low channel resistance. And last, regarding to the gallium arsenide power device, although the gallium arsenide material has been very tremendously studied in the last 10 years, and also because due to the mature of these materials, and then people start to demonstrate all kinds of the gallium arsenide power diodes as shown here, and also the power MOSFET. So power diode is including the typical vertical Schottky barrier diode and even the PN diode or the JBS diode. All this has been demonstrated with very high performance. And regarding for the MOSFET, so people also start to demonstrate, for example, this field plate MOSFET, and also with this heterojunction FET. And also recently, people try to develop this lateral MOSFET and the vertical MOSFET. So in the later talk, we will share some of the recent progress, very highlighting advancement in the gallium arsenide power device. So one thing is interesting to look at the cost comparison between the gallium arsenide and then the silicon carbide wafer. So this is considering for 6-inch gallium arsenide wafer. So we can find out that one of the most attractive point for gallium arsenide is that it can possibly to achieve the very high voltage with low resistance compared to similar like the silicon carbide. And another very big advantage is that we can highly reduce the cost. So you can see the silicon carbide cost is around here. But now, if we gradually to improve the gallium arsenide towards the mature process, mature epitaxy and large wafer size, and therefore we can reduce gallium arsenide cost significantly. So then in the next part, I will start to report the recent advance in the gallium nitride, silicon carbide, and gallium arsenide power device. So the first one is a wafer size evolution. So as you know, to complete the silicon power device, the major issue for all these wide bandgap material is cost. So therefore, one important thing to reduce the cost is to try to grow a large wafer size here. So now we can see this is a STM microelectronics has to demonstrate for the 8-inch silicon carbide wafer in the last 5 years, and then it's getting more and more companies start to moving to have the 8-inch silicon carbide wafer. And regarding to the GaN, so the 8-inch in GaN on silicon wafer is already on the market at this moment. And recently, the Intel also demonstrated the 12-inch GaN on silicon wafer. So that's actually make the gallium silicon technology very attractive. And the last one is in the right-hand side for the gallium arsenide wafer. So right now, the 4-inch gallium arsenide wafer is already commercialized, and 6-inch gallium arsenide wafer is in the R&D phase. So the first recent highlight in the gallium nitride technology is integration of a diode. In the past, typically we consider the GaN hand as a discrete semiconductor. So that means we have to fabricate the standalone p-GaN hand and then to have another standalone diode, typically using the silicon carbide diode. But however, if we try to connect this discrete GaN and then discrete diode, and then we need to very complicated packaging and also additional connection that can cause a lot of parasitic inductance. And therefore, if we can try to fabricate a diode with the same epitaxy using the p-GaN hand, and that can actually fully to realize the integrated circuit. So this is a recent one demonstration that the p-GaN hand and then shunting barrier die can be fabricated side by side using the same process with the same epitaxy wafer. And then in this case, we can start to realize the integration of the SPD and p-GaN hand together. And therefore, that start to push the technology towards what we call the GaN IC direction. So in the past, if we consider high side, low side switch, then actually we need the 3 dies. We need to high side transistor, low side, and then also the driver. But nowadays, people try to integrate these two together. So we can have the driver with a high side integration or low side with a low side switch, or we integrate high side, low side together with another additional silicon driver here. But in the future, now it's happening now is we try to integrate everything inside the GaN hand platform. That's why we call it GaN IC. And in this case, we can only need one die that fully cover all of the gallium nitride function and gallium nitride electronics. So this is one of the demonstrations in the several years ago from IMEC. They have demonstrated all GaN IC technology. So in order to realize this all GaN IC technology, actually the GaN IC platform needs not only for the high voltage enhancement device, we also need high voltage DMOS, high voltage Schottky diode, and also many low voltage devices that allow us to realize the GaN IC platform. So in this paper published several years ago from IMEC, and has been demonstrated not only for the high voltage power device, but also for the logic device like the RTL and DCFL. These are the logic functions has been demonstrated in this GaN IC platform as well. And also, in order to realize the real GaN CMOS, we not only need the electrons, we also hope to have the holes in the gallium nitride epitaxy. And then therefore, in the world, there are many, many researchers trying to grow the 2D whole gas in the gallium nitride hand epitaxy. So by leveraging these 2D whole gas, it's possible to demonstrate this typical CMOS characteristic. So that can actually be the very attractive development for the next generation GaN IC. And also, in the several years ago, the Intel also demonstrate another approach by trying to using the silicon CMOS bonding with the gallium nitride. And you can see this is fabricated on the 300 millimeter gallium nitride hand epitaxy, and then another silicon CMOS is bonding on top of a GaN hand. And in this case, we can realize the current capability for the GaN ham and then the PMOS can be very similar, and that's good for the CMOS operation. And also another development trend is to try to fabricate the GaN ham towards very high voltage application. So this is some demonstration to show that gallium nitride power hand with a proper buffer thickness and then the substrate engineer is possible to demonstrate more than 1,200 volt capability. So in left-hand side, this is demonstrated by my group that we have fabricated the gallium nitride power hands on QT substrate and with the highest breakdown up to more than 2,000 volt. And also in the several years ago in the ISPAD 2022, the transform also demonstrate the 1,200 volt GaN switch on the sulfide substrate. And another development trend for the gallium nitride is try to have the vertical gallium nitride MOSFET, but the typical full vertical GaN MOSFET needs a GaN-on-GaN, this homo epitaxy. But the GaN-on-GaN substrate has a huge limitation of a wafer size and then very high cost. So therefore, people think about maybe we can also use a typical GaN ham epitaxy, and then we fabricate the vertical trench MOSFET. But in this case, we call as a semi-vertical because the drain side is not really in the bottom. The drain side is in the side wall, as shown here. So this wall is demonstrated by IMEC in the 2023 for the semi-vertical trench gallium nitride MOSFET, and this wall has been demonstrated on the 200 millimeter GaN and QT substrate, and then breakdown voltage can achieve for more than roughly around 800 volt, and then with the higher threshold voltage up to 2.9 volt. Of course, the best case that will be if we can fabricate the fully vertical GaN trench MOSFET. So this was demonstrated by the Toyota in the 2019. They fabricated the fully vertical gallium nitride trench MOSFET with a breakdown voltage more than 1,000 volt. And also in the last year, IEDM, the Professor Kevin Chen from the Hong Kong HKUST Hong Kong University, they also demonstrate the hybrid FET by combined with the gallium nitride hand with the silicon carbide drift region. So as you can see the device structure here, this is a vertical transistor, and then the drain is in the bottom side, and then the silicon carbide N-drift region is used to sustain the high voltage drain. And once the current flow up to this layer will start to go through the gallium nitride hand. So the upper part is a gallium nitride hand. So this is the first demonstration to combine the GaN hand with the silicon carbide. And this can overcome several difficult challenges in the conventional GaN hand. For example, it can exhibit enhanced mode operation, Also, it's important to have a non-destructive energy breakdown and also negligible dynamic R and also a very stable threshold voltage. And regarding for the silicon carbide transistor, so the conventional silicon carbide MOSFET still will be used as a planar MOSFET as a main structure. But now people start to try to reduce the low resistance, so they will start to fabricate the silicon carbide trench MOSFET, and that can reduce the channel resistance. But the problem is that once we make this trench gate, and usually we easily to have the high electric field around this gate corner, and that can cause a lot of reliability issue. So that's why so far, not that many companies can successfully commercialize the silicon carbide trench MOSFET. And also, in order to continue to improve, to reduce the resistance, so super junction is necessary, has to be considered. So this is demonstrated by the AIST in ISPAD 2020 by using this multiple epitaxial growth method to realize this trench super junction MOSFET. So because usually if we want to realize this the super junction, we need to form this PN lock here. But usually we cannot have this mega electron volt implementation, or it's very difficult to have this trench filling. So therefore, the AIST proposed this multiple epitaxial growth method. And in the end, they can successfully demonstrate the super junction, vertical silicon carbide super junction MOSFET with a perfect PN junction pillar. And the most important is that you can see here the super junction U MOSFET can further reduce on resistance with the same voltage rating compared to the typical U MOSFET. And also, another very interesting development directions in the past will be the silicon carbide integrated circuit. So in this work, this work reported the integration of the 10-volt CMOS logic circuit, 20-volt gate driver, and 600-volt VD MOSFET on silicon carbide single chip for full silicon carbide small power IC application. So that's also demonstrate that it is possible to realize a silicon carbide IC. And also in this year ISPSD also the vertical channel thin silicon carbide MOSFET has been demonstrated. That's target for the 3.3 kilovolt application. And we can see by consider this vertical channel thin silicon carbide, we can further reduce on resistance and also to have very high breakdown voltage. So that's very promising for the 3.3 kilovolt application. And regarding for the gallium arsenide diode, also in the last several years, many traumatic progress in the gallium arsenide device. The first one, people pay a lot of attention to fabricate a high performance gallium arsenide Schottky barrier die. So in this work, is featuring with nickel oxide, P-type nickel oxide as a junction edge termination and on top of the main substructure to alleviate the electric field. In the end, can demonstrate more than 2000 volt breakdown voltage. And also, the vertical trench gallium arsenide MOSFET has been demonstrated recently. So you can see the structure here is very similar to the silicon carbide trench MOSFET, but now it's demonstrating the gallium arsenide with considering the aluminum oxide gate dielectric, and the result shows that the device can exhibit for more than 1000 volt breakdown voltage capability. And not only for the vertical gallium arsenide on gallium arsenide power device, recently the gallium arsenide growing on the sulfide substrate also attract lots of the attention because this can highly reduce the cost and also to avoid the epitaxy issue. So this work is demonstrated by our group and then with Professor Hong group to focus on the MOCVD grown gallium arsenide power MOSFET on carbide with in situ silicon doped. So in this literature, we reported with the later the gallium arsenide power MOSFET growing on sulfide, and with considering the different silicon doping, so the device can actually exhibit quite decent IV characteristic, and also the good breakdown voltage can be up to more than 450 volt. And also in this year, Professor Hong group also demonstrated a very novel approach by using the gallium arsenide also growing on top of the sulfide, but also with using the implantation to realize the P-type gallium arsenide. And after realizing that P-type gallium arsenide, start to regrowth the N-type gallium arsenide to fabricate the real PN diode in the gallium arsenide material systems here. So in this case, the gallium arsenide PN diodes can be successfully demonstrated with turn-on voltage around like 4 volt. And most importantly is the breakdown voltage can achieve more than 900 volts. So that's a very promising demonstration that the gallium arsenide can be grow on top of sulfide substrate that can be considered as a low-cost approach, and also by considering this P-type implantation to easily realize the PN diode in the gallium arsenide transistor and gallium arsenide diode. Final is a conclusion. So this is a general comparison between the y-axis is output watt, and then also the x-axis is a switching frequency. So basically, the gallium nitride is target for the low watt, low output power, but with a higher frequency application. And then silicon carbide is target with a medium frequency, but with a high power application. And gallium arsenide can be considered to target with even higher power application, higher than the silicon carbide, because of due to the very wide bandgap of the gallium arsenide materials. So silicon carbide, gallium nitride, gallium arsenide are important enablers for our future green economic and high performance silicon carbide, gallium nitride, gallium arsenide power device has been demonstrated beyond silicon power device capability. And also it's important to know that the large wafer size development in these three materials are actually very crucial for the cost reduction. And the last thing is not covered in today's talk is reliability. Reliability still remains the main concern for all these three wide bandgap materials and needs to be carefully evaluated and understood. Okay, so that's ended my call, and thanks for your attention.